All right, we got a short, very short little video here. We're going to be talking about the mean and standard deviation, mu and sigma, of a binomial distribution. This is actually going to be pretty easy. It's almost like you can just think about and at least get the mean on your own without really needing the formula that we'll discuss. So the one example we're going to look at here, or really to begin our example, says if you make 75% of your free throws and someone asks you, well, out of 12 shots, how many would you expect to make? Well, I would expect to make 75% of my 12 shots, right? So 75% of 12 shots would be 9. I would expect to make 9 shots out of my 12 if I'm a 75% free throw shooter. Well, the 9 shots that I would expect to make, that's my mean. And since we are dealing with a binomial distribution, I have two outcomes. I'm either going to make it or I'm going to miss it. My shots are going to be independent of each other. I have a fixed number of shots, and my probability of success, I'm going to assume, stays the same at 75%. So I do have a true binomial distribution, and so the formula that we're going to use for the mean is the number of trials, which in this case was the 12, times p, the probability of success, which was the 75. So 75% of 12 gave me my 9 shots, and that's the mean. Okay, so that's pretty easy. Now, the standard deviation, on the other hand, not quite as straightforward, but here's the formula that we'll use, which is the square root of n, which would be 12, times p, which is the 0.75, times the probability of failing, 1 minus p, which would be 25%. Okay, so I'm not going to actually calculate that. We'll actually go through this full example here. So it says when an opinion poll calls residential telephone numbers at random, only 20% of the calls reach a live person. You watch the random digit dialing machine make 15 calls. Let X equal the number of calls that reach a live person. So to find and interpret the mean, all we're going to use is the n times p formula. And n is our number of phone calls, which we're making 15. And p is our probability of success that we actually reach a live person, which is 20%. So 20% of 15 phone calls is 3, exactly. I would expect 3 of my 15 phone calls to actually reach a live person. Now, to interpret the 3, this is what we would say. We would say we expect 3 of the 15 calls to reach a live person. Now, I have seen in the past where some people start to get a little sloppy, and they say we expect 3 calls to reach a live person. But you have to say kind of what's your denominator there, 3 out of how many, so don't just leave that part out. Say how many out of how many that you would expect to happen. All right, standard deviation. So we've got the square root of n, which again is our 15, p, which is 20%, and 1 minus p would be 80%. So if you throw that in your calculator, you should get 1.549. Okay, if I rounded that to 3 significant digits there, or 3 decimal places rather. Now the interpretation part, again, this isn't as straightforward as what you might think it is. So we would say, if the machine called 15 random numbers many times, so calls 15, calls 15, calls 15, calls 15, calls 15, calls 15, etc., the number of calls that reach a live person would differ from 3, and 3 being the mean, by an average of 1.549 calls. So sometimes we might call and we get 4 live people. Sometimes we might call and get 5 live people. Sometimes we might get 2. Sometimes we might get 1. Other times we'll probably get exactly 3. Okay, so the average amount that we're away from the mean, which is the definition of standard deviation, is about 1.5 calls. Now here's the only other example we're going to look at, and we're done with the video. A manufacturer makes light bulbs and claims that their reliability is 98%. Reliability is defined to be the proportion of non-defective items that are produced over the long term. If the company's claim is correct, what is the expected number of non-defective light bulbs in a random sample of 1,000 light bulbs? So we want to know the expected number. The expected number is the mean, and the mean is, in this case, n times p. Okay, now first we have to make sure this really is a binomial. So is this a binomial? Let's see. Is there a fixed number of trials? Yeah, we have 1,000 light bulbs. That's a fixed number. Is the probability of success constant? Yeah, they said it over the long run, it's 98%, so we're good. Are bulbs independent? And we're going to assume that they are. And last but not least, two outcomes. Well, they're either going to be defective or non-defective. So yes, there are two outcomes. So this is in fact a binomial distribution, so we may use the n times p formula. So n is our 1,000 light bulbs. Our reliability is 98%, so 0.98. And so 1,000 times 0.98 is 980. We would expect 980 to be non-defective. Now you got to watch out because I could have said, what is the expected number of defective light bulbs? And then the answer would be 20 instead of 980. So it is important to watch out for what exactly the question's asking for. So the answer there would be D. So we would expect 980 light bulbs out of 1,000 to be non-defective. And so that is all for this video. I promise you it'd be short. So in addition to this video, you also have 3 other problems to do. They are on your outline. So take a look at those after watching the video, and we'll talk about them tomorrow in class. That is all. Adios and goodbye.